Yeah, is it over now? Sorry for the inconvenience. Yeah, good evening, everyone. It's already delayed. Okay, let's start the session. So, please check the assignment questions. I'll share in that CMOS module. Okay, we'll start the session. So, today we'll discuss the thing related to how we are constructing CMOS. Am I audible? Hello? Yes. Okay, okay, okay. Fine, fine, fine. Okay, the complete construction of CMOS, how we fabricated the CMOS layer by layer. Okay, and starting coming to the first slide. So why we are using CMOS rather than BJT or some other electronic devices? Because so see, check here. Here CMOS is the why we are using CMOS means this is the key advantage, right? Integrated both NMOS and PMOS on the same wafer, right? So this is my VDD means, okay. So this is my VSS, okay. In between these, we are checking for output, okay. And this is my PMOS and this is my NMOS, right? So here we are having source and and drain and source, correct? So here this is the NMOS, sorry, PMOS, and this is the NMOS. So we are integrating both on a same wafer, right? This is the complete CMOS structure, right? So this is why we are using this means this is low for low static power consumption, because so when we are giving the logic, so when we are applying the logic one, so this is completely off and it cannot deliver this VDD to the output side, right? When we are applying zero only, this when we are applying zero only, this PMOS will on, and then only there is a one connection from VDD to output and it will pass the VDD. Okay, then we can get the output as VDD, right? So this is the basic operation of CMOS, okay. And for one logic, this is completely in off condition, correct? So when we are switching on the device, then only it will deliver the logic, right? So for the another case, we can save the power, okay. And CMOS means complementary MOS, and the major problem is high power dissipation in circuits using only NMOS or BJT. That's why we are using CMOS. Clear? And this is faster execution. Okay, this is the up to CMOS slide, and we are having three methods for CMOS fabrication. So CMOS fabrication means how we are fabricating the complete electronic component of CMOS, and how we are depositing the metals, and how we are creating gates, substrates, and wells. I'll explain now. Okay, so here we are having NWEL or PWEL technologies. Okay, which means N-well diffused into P substrate, or P-well diffused into N substrate. This is how we are creating NMOS and PMOS, right? So, and we are having another process like twin tub also. Twin tub means we are using N-well and P-well in the both the things. We are having one epitaxy. See, when we are need to construct one twin tub process, then in between that we are having one epitaxy layer. Okay, so we can construct both the PMOS and NMOS at the same time by using this twin tub process. Okay, twin well, or we can say that twin tub also, correct? And we are having another one also, silicon on insulator. So this is mainly used to improve some speed and eliminate some latch up issues. Okay, latch up issues means, so when PNP and NPN transistors, okay, when these transistors are connected back to back, okay, then one straight path is formed from VDD to ground. So because of this latch up issue, there is a more power consumption happens. Okay, there is one direct path from VDD to VSS, so more leakage power also happens. That's why we are not we can avoid this latch up issues. Okay, this is the thing. And these are the three methods how we are fabricated a CMOS. Done. Shall I move? Is it clear, guys? I don't know whether the screen is visible to you properly or not, because I'm facing some issue like I cannot share my PPT screen only. That's why I'll share the complete entire screen. Is it clear? Okay. And so this is the process NWEL and PWEL technologies. Okay. So for constructing N-well, okay, so we need to diffuse the N-type well into a P substrate. So if you want to construct one, this is my P substrate. Okay, this is my P sub. Okay, in that I need to create two wells. These are N wells. Okay, this is how we are generating N wells, and after that P wells also, vice versa. Here for creating P wells, we need to take N substrate. So for taking N substrate, again we need to construct the P wells in it. Okay, the main goal is to create the body for the complementary transistor. Okay, and P substrate plus N well, which means the platform for PMOS. This is the PMOS, right? This is my PMOS, and same as to generate NMOS. Okay, generate NMOS, we need to take first N sub. Okay, this is my N substrate, and again we need to do P wells in it. Okay, and in between both of them we are having one gate terminal, right? I'll explain in the next slides how all this process is constructed and all. Here also you are having one gate terminal. So this is my PMOS and this is my NMOS. Clear? This is the thing what actually happens, and this is how we are constructing and we are creating CMOS. Okay, and this is the first step. Okay, first step is substrate selection. So here I selected P substrate, which means P substrate means which one it was? I'll choose here P substrate, right? Right, because NMOS. Okay? NMOS or PMOS? Clear to everyone? Okay? So it, as you said, like, so function acts as the common body for NMOS, right? So we need to here again construct the N wells here, okay, in P substrate. So choose first we need to select the base material, okay. So for we need to construct one NMOS, then we need to choose P substrate. If you want to design a PMOS, then we need to select N substrate, right? So here we are selecting my base material, which means P-type silicon substrate, okay. So it is typically one we are having some boron dopants also here, okay, for the electronics and holes concentration. So it is acts as the common body for NMOS and the base for the N well. Okay, if you want to construct wells means we need to take first select substrate, right? Clear? So here I'll choose my substrate. Okay, this is the first step, and after that oxidation. Okay, here we are applying the SiO2. So this is my S pink one is my SiO2 layer. Okay, so this process is known as thermal oxidation. Okay, so by using some oxidation chambers, okay, this is the condition high purity oxygen or hydrogen we are using while applying this oxidation layer, okay, which results the silicon dioxide, right? SiO2 means silicon dioxide, so grown on the surface. So this is my substrate means this becomes my this is my substrate means this becomes my surface, right? So here I'm using SiO2 for my surface, okay. And what is the purpose for adding this layer means it acts as the barrier to protect regions from contamination and future diffusions, okay. If you want to add any diffusion layer, this oxidation layer will protect, okay, for gate and the substrate layers, okay. So this is the second process, this is the second step, oxidation step. So in oxidation step we are creating one layer, okay, one surface layer. For that surface we are using silicon dioxide, okay. And this is the second step, and after that we are having growing of photoresist. So after applying the SiO2 we need to again make a layer of photoresist. So this is the process of photolithography preparation. So for creating wells we need to apply some photolithography process. So before doing photolithography we need to have one photoresist layer, right? So this is my yellow one is my photoresist layer, okay. The wafer is coated with a uniform film of photosensitive. This is my photoresist layer, right? So for you while we are applying or okay, while we are applying the light, this photo because of this photoresist we can construct the wells, okay, by using this photoresist layer to enable selective etching of the SiO2 layer. So for SiO2 layer, when we want to etch the SiO2 to form a wells and wells, we need some photoresist, okay. This is the layer, and this is the third step. This complete process is known as photolithography process, okay. And after that, step 4. So in this step, after after applying photoresist we need to we need to pass some UV rays, okay. By you the UV rays will directly affects on the photoresist. So this is the process after photolithography. Okay, a mask is placed over the photoresist. So here we are having one mask also. So this complete wafer is exposed to UV rays, right? This mask is completely, observe here, this mask is completely affected to UV rays. So then what happened? Photoresist under the transparent regions of the mask get hardened, right? So when we are applying these rays, okay, then the transparent regions of the mask will hardened, okay. And this is the thing happening here. And after applying the photoresist, we need to apply mask. So here, this is my mask, okay. So after that, we need to apply some UV rays, okay. So after applying the UV rays, the rays which passed through the mask will be get hardened, okay. And after that, see, where we are applying the mask at this at that space only, here, check here, one well is created, right? So here, removal of unexposed photoresistor, okay. In this we need to what exactly at the place of mask, that completely space is removed, right? So this is the process of developing and dissolve the unexposed photoresist. Here we are unexposed the photoresist, right? So after that, what happened? The hardened photoresist remains and creating a protective pattern. The remaining will be the same, okay. Understand? This is the first step. And after that, removal of photoresist layer. So after creating this well by using some UV rays, particularly at the mask, okay, and we need to remove the remaining area of photoresist, right? We are completely removed this photoresist layer because we are get the result, right? And after that, H2SO4 sulfuric acid by using this chemical process. So what we removed that photoresist layer, okay, by using this acid, and remove the hardened photoresist mask, okay. Check here, it will remove the remaining photoresist mask, right? The patterned SiO2 layer remains on the wafer. So after removing the, see, after removing my complete photoresist layer by using this sulfuric acid, then what happened? The SiO2 layer remains on the wafer, okay. And after that, formation of N-well. This is what's happening here. So the process of diffusion or implantation. So here we are diffuses one N-well, okay, into my P substrate, okay. And N-type impurities, like these are some phosphorus, arsenic. So which group of atoms are these? Fifth group or third group? Any idea? Yes, ultraviolet radiation. Yes, Dinesh and Vikas. So these are my pentavalent atoms, right? And diffused into the exposed P substrate region. So by using some diffusion methods or else implantation methods, we are adding one N-well impurity into the P substrate. Okay. So after that, an N-well formed inside the P substrate. So this my blue colored one is complete my N-well, right? So we are created a well by using some pentavalent impurities, okay. Then we can form one n type impurity by adding some n types impurities. We can form an n well in the P substrate, okay. And this is the thing happening here. What happened? Okay, no issues. So this is my fifth step, removal of SiO2. So up to now we removed the photoresist, so we are having only SiO2. So in this step we are removing that SiO2 layer also, right? We are having one layer here, right? So we are removed that layer also, okay. by using some hydrofluoric acid. Okay, the remaining SiO2 layer is completely removed. Okay, understand? We have completely removed the, actually this one acts as the diffusion mask, right? So we are completely removed that one. And what we can observe, silicon surface with N well diffused in specific area. Okay, for a particular area we observe N well in the P substrate. Okay, and after that this is my step and deposition of silicon. So after creating my well, then I need to deposit the gate and polysilicon, right? So here we are creating the complete gate. Here we are, this is the process of aligning gate. Okay, so why we are using here gate? So to prevent the misalignments which could cause unwanted capacitance. So if you are having any unwanted capacitance in our design, okay, in the gate level, then it can leads to some delays, right? So that's why we are here we are applying the at the gate terminal only we are applying the logic also, right? And this is the process of grow a thin gate oxide layer. So here we are by some metal deposition techniques we are creating one thin gate oxide and deposit polysilicon via chemical wafer deposition. Okay, this is the process of creating. Well, we are creating this polysilicon layer, then we are using this chemical wafer deposition process. 1 minute, guys. Understand? So, and why we are using polysilicon? Oh, where it was? Okay, this is the thing why we are using polysilicon. So when we are having high temperatures, when we are having more than 800 degrees Celsius, okay, so this layer will protect us. Okay, protect the transistor. And this is the process of how we are creating polysilicon and thin gate oxide. So if anyone asks like how we are creating polysilicon means, when by using some chemical wafer deposition steps we are created polysilicon. Okay, and after the formation of gate region. Okay, so by using some etching process, okay, by using the etching process, etching of gate, okay, polysilicon is selectively etched away. So first we are having completely gate layer and some poly layer, right? So where we want gate, where we need gate, actually we are having P substrate and N well, right? So again, so we need to take one again. Also we are having two wells here. Okay, and here also we can get two wells right here. Okay, so one is my source and the drain, and here also one is my source and one drain. So in between source and drain we need to take gate terminals, right? So this is the process of selecting gate and poly, where we want by using this etching process. Okay, by using this etching process polysilicon is selectively etched away. So where we want my gate terminal, okay, the gate terminal remaining part will be removed. Okay, only the polysilicon remains over the gate oxide in the transistor channel region for both PMOS and NMOS. Okay, PMOS also having source and drain, NMOS also having source and drain, right? So in between that we need to have one gate. Okay, this is the process how we are creating gate. Okay, and after that oxidation means it acts as the one of the protective layer. Okay, by using some deposition of metal. Okay, by using some deposition of SiO2, sorry, and an oxidation layer SiO2 is deposited over the entire wafer. So from here to starting of the substrate to here, okay, we are depositing SiO2. Okay, so before also we are adding SiO2, but we are removed that layer, right? So in this again we are after creating the gates, again we are depositing the SiO2. Okay, it acts as the shield for diffusion and metallization steps. Okay, in metallization steps we are creating the terminals, right? So to affect does not affect to the n well or p substrate, we are depositing the SiO2 layer here. Understand? This is the process of complete oxidation. And after that, n-type diffusion. Okay, this is my n-type diffusion. N-type diffusion means source and drain for NMOS. This is my complete NMOS, right? So this is the process of making deposition and implantation. Okay, and small gaps are open in the oxide. So these small gaps, okay, here we can observe the gaps, right? And n-type impurities are diffused. So at this particular places, my n-type impurities are diffused. Okay. So result three n plus regions are developed. Here we can observe three regions, right? Here one, two, and three. So in these three regions, we are adding some n-type impurities in it. These forms source, drain, and body contact for the NMOS transistors. Correct? Understand? So this is the complete process of how we are creating source, drain, and body terminals by adding some n-type impurities, where we can observe some small gaps in between the oxide. There we need to diffuse the n-type impurities. Understand? So after that, see, check here. So this is my p substrate, right? That's why I need to well n plus and n plus wells regions. One is for source, another is for drain, and the remaining is for body. So here is my n well, right? That's why we need to diffuse the wells with p type. This is one of for source, and the another one is for drain, and this n plus is my body. And p-type diffusion, similar masking process for the PMOS side. So here we are having two sides, right? P-type impurities boron are diffused into the end well. So here check here, and it results the P-press regions for source and drain. Okay, and after that what happened? So the deposition will happen, okay, by using some material like thick SiO2. Again we are using SiO2 for protective layers. Guys, are you there? Are you with me? Understand? We are up to now. Okay, so again we are applying the SiO2 layer. Actually SiO2 layer is acts as the protective layer, right? So this is how after creating source, drain, and body terminals. Okay, after source, drain, and body terminals in p substrate and n well, so again we need to apply SiO2 layer. Okay, and what it will do, covers the region of the wafer where no metal remains are required. So wherever we does not require the metal for actually this place is mainly used to create the terminals, right? While we are depositing the metal, this space is used for depositing the terminals, right? So the remaining space we are filled with SiO2. Okay, and this is how we are creating one field oxide. Okay, and it prevents short circuits and provides insulation. So to avoid the issues from terminals, in between the terminals, so here we are having some terminals, right? In the metal deposition process we can get some terminals, right? To avoid some short circuit issues, we are creating this SiO2 layer again. Okay, and this is the thing happening up to now. And after that, metallization and terminal formation. Okay, so in this process, okay, this complete, where is my pointer? Okay, here. So this is my complete aluminum. Okay, we need to fill our complete wafer. This is my complete wafer, right? So we need to fill the remaining part of our wafer with this aluminum. Okay, this process is known as metallization. Okay, and this is the 17th step, and after that we need to remove all of excess metal. After that, so here we need to take some terminals, right? So all these are my terminals. So it, after doing the metallization, we need to remove the metal from undesired areas. So after applying the aluminum in the metallization process, so after completion of this metallization, we need to remove the remaining one. So this complete in the metallization process, we are creating a source, drain, and a gate terminals, right? After creating the terminals, we need to etch the remaining part. Okay, so this is my step, and after that, this is my 20th step, aging names. Terminals are labeled as here. We are labeled. So this is my body, and this is my source, drain, and gate. So after doing metallization and after that etching, we need to name it. Okay, this is my source, gate, drain for and MOS and PMOS. So this is my complete inverter structure. Okay, so how a inverter structure will work? So this is my VDD, and here we are having VSS, right? So this is my PMOS, and here also we are having NMOS. For both the terminals, we need to connect one gate here. Okay. So for this is my PMOS, and this is my NMOS. Here source, drain, and drain, source. Okay. So here we need to check for output, right? So for inverter, A is my input and Y is my output. Correct? So when we are applying zero, what happened? When we are, where is my pointer? Okay. So when we are applying zero at the gate, okay, what happened? Then this PMOS will turn on. Then a direct path from VD to V out. Then we can get the output as 1. Okay, so again I am applying my logic as 1. Then what happened? So this PMOS is in turn off and NMOS will be in on. So there is no connection path from VDD to V out, right? So that's why I can get my output as 0. Understand? This is how a complete process of, okay, this is how we are creating one transistors. This is the fabrication process. Understand up to now? So like this manner we need to construct. I'll give assignment questions to generate to construct one twin tub process, or else I'll explain the twin tub process, and you need to take one what NMOS construction and PMOS construction separately. This is my complete inverter, right? This is my complete inverter process, right? So I'll give some assignment questions to you. Wait, I'll explain from starting briefly if anyone joined late. Okay. So for fabrication processes, we are having three methods. First one is NWEL or PWEL technologies, or using twin tub process, or else by using some silicon on insulator also we can do fabrication process of CMOS. So in first step, we are having some NWEL or PWEL technology basis. Okay, for generating NWEL, we need to choose a P substrate. Okay, for PWELs, we need to select N substrates, and one P substrate and NWEL is known as PMOS, right? PMOS transistor. And actually, we here we select P substrate, right? So, and first we need to select the base material. Okay, after that we are doing in oxidation process oxidation layer we are applying. This is SiO2 layer by using some thermal oxidation or oxidation chambers. We are applying this layer. So after that, we need to apply the photoresist. Okay. So after applying photoresist, we need to give the mask and UV rays. So here my complete wherever we are having mask, their part only etched here, right? This part is etched. So after that, we need to remove the photoresist also, correct? So after that, we need to place N well by using some N type impurities like pentavalent. Okay. And after that, we need to again remove the oxidation layer. Okay. So after removing the oxidation layer, again we need to apply some gate oxide and polysilicon. This is completely for gate terminal, to create gate terminal. So this is how we are creating our gate terminals. So after that, again we need to deposit the SiO2. Okay. And after that, wherever we are having some remaining spaces, those spaces are for source, drain and body. Okay. So this is how we are creating source, drain and body. Okay. Again we need to deposit one SiO2 layer. And finally we are having some metallization step. Okay, this is my metallization step. We completely filled the wafer with aluminum. So wherever we required my terminals, and the remaining part will be etched off. Okay. And after that we have to give the names. Okay. So this is the thing happening here. This is my complete CMOS inverter. So in CMOS inverter we are having NMOS and PMOS terminals. This is how happening. And any doubts up to now? So this is the thing, guys, up to now. So we need to construct the NMOS and PMOS separately. Okay, by using the same process. Dinesh, you are having any doubt or else what? Comment now. So please check the assignment questions. I'll upload the assignment questions on the some CMOS basics. Try to answer those questions. Those are some basic questions only on the first day of introduction class. And again, I'll upload the assignment questions again for the construction of NMOS and PMOS separately by using the complete process. So every day we are having class by 6 o'clock, guys. Please try to join. Okay, we remind or not, please try to join the class by 6 o'clock. Okay, I think we are having CMOS classes for 1 week. Okay, I'll try to cover whatever the things you guys required. Okay, for DV people. Anyone having any doubts? So after completion of CMOS module, we'll conduct one test on complete CMOS, and I'll prepare some interview questions also for this particular CMOS subject. Okay, I'll share in the LMS portal. So clear up to now, or else having any doubts? So please try to convey with your friends also to join the class exactly by 6 o'clock. Anyone having any concerns or any issues? If I'll start class by exactly at 6 o'clock or else by 6:10. Okay, let's wind up the session then. If you are not having any doubts. Okay, guys, thank you. Have a good day. Bye bye.